All right, we've already looked at finding some x-intercepts in polynomials by setting their factors equal to 0, but we want to carry those factoring methods a little further in this lesson. We want to look at how to solve polynomials by factoring and look at some of the more complex polynomials. So we're going to start here with the 2x cubed minus 5x squared minus 3x is equal to 0, and I want to factor this polynomial. So the first thing I'm going to do is look and see, do I have any common factors in my polynomial? So 2x cubed minus 5x squared minus 3x equals 0. Do I have any common factors in this polynomial? And I do. The common factor in this polynomial is x. So I'm going to factor it to the front. So x, and then what do I have to multiply x by to end up back with my original? Well, 2x squared minus 5x minus 3. I've simply factored out the common factor. Remember, always factor out the common factor first. Well, I still don't have a value where a is equal to 1, and I have no more common factors. So let's review our method for factoring that type of a quadratic. We can multiply a times c, so 2 times negative 3, and that gives me negative 6. I'm just multiplying those two terms together. So I now need two factors which multiply to give me negative 6 and add to give me negative 5. Well, that would be negative 6 and positive 1. So I can rewrite this as 2x squared minus 6x plus x minus 3. So I have now set this as a polynomial, this quadratic piece of this, and I have simply split that center term into two terms. So now, look for common factors in the first two. Well, what can I take out of 2x squared minus 6x? I can take a 2x. So this becomes 2x times x minus 3. Then I look at the last two terms. What can I take out as a common factor? Well, there's nothing there. Nothing that I can pull out. But I can't just make that 0. I need to end up back where I started. So this is a plus 1. If you can't find anything else to take out, you can always take out a 1. And that leaves me with x minus 3. Do I have the same thing in both sets of parentheses? I do, which is what I really want to happen. So I have a factor left over up here of x, and then this quadratic factored as what's not in the parentheses, 2x plus 1, times what is in the parentheses, x minus 3. So now, in factored form, this polynomial is x times 2x plus 1 times x minus 3. Well, what do I do with those? If I'm trying to solve by factoring, I set the factors equal to 0. So x is equal to 0. And 2x plus 1 is equal to 0. Well, you'll quickly learn to do this in one step, but I'm going to take 2. Subtract 1 from both sides, and 2x is equal to negative 1. Then divide both sides by 2. X is equal to negative 1/2. So there is one of my zeros or my x-intercepts in my polynomial. And then finally, x minus 3 is equal to 0. Add 3 to both sides. X is equal to 3. And I have all of the solutions, all of the roots, all of the zeros of my polynomial. Now, are they all real numbers? Yes, they're all real numbers. So how many x-intercepts do I have? I have 3 x-intercepts. 2x cubed, it's a third-degree polynomial. So I have, in this polynomial, 3 x-intercepts, 3 solutions. All right, let's look at one. Then first of all, we need to use a little different method to factor and does not have the same number of x-intercepts as it does solutions. And I bet you can figure out before I even start how that's going to happen. So let's use this polynomial. X to the 4th minus 3x squared equals 4. And I want to solve this by factoring. What do you think I'm going to do first? Well, obviously I need to put it in standard form. So x to the 4th minus 3x squared minus 4 equals 0. Well, I'm going to use kind of a strange little method to solve this. Do I have a common factor here? No, because there's no x in this 4 term. this is what's called a quadratic form of a polynomial, even though it's not a quadratic. It's x to the fourth, x squared, x to the 0. When that happens, if I can turn this into something squared, then I can factor it as if it were a regular quadratic. So what I'm going to do is I'm going to come out here and I'm going to use u. And I'm going to say u is equal to x squared. And then I'm going to rewrite this. So if u is equal to x squared, then x to the fourth would be what? X to the fourth would be u squared. Right? Does that make sense? I'm going to square both of those. So x to the fourth is equal to u squared. So I'm going to rewrite this as u squared minus 3u minus 4 equals 0. Doesn't really matter which variable I'm using when I write that. So can I factor that? It now becomes pretty simple to factor. I have u minus 4 and u plus 1 equals 0. So set the factors equal 0. U minus 4 equals 0. U is equal to 4. And u plus 1 is equal to 0. U is equal to negative 1. Now, I'm not done, because remember, I replaced my x squared with u, so now I have to go back and undo that. I have to go back and make these u's back into x squareds. X squared is equal to 4, and x squared is equal to negative 1. So if I want to find the value of x here, I take the square root of both sides in both of those equations. X is equal to plus or minus 2, and x is equal to plus or minus the square root of negative 1. How do I want to write that? I want to write that as plus or minus I. Alright, so my solutions to this are x is equal to positive and negative 2, x is equal to positive and negative I. How many zero solutions roots do I have? I have 4. 1, 2, 3, 4. X to the fourth. I should have 4. But how many of them are x-intercepts? Well, only these 2, because these 2 are not real numbers. All right, we'll graph this. If you graph this with your calculator and look, you'll discover that you have x-intercepts at x equals 2 and x equals negative 2. Yet this is an x to the fourth function. What does that tell me? It tells me that there are imaginary roots that do not appear on the graph. If I only have 2 x-intercepts and they're not bouncing off the x-axis, which tells me they have a multiplicity of 2, then probably there are imaginary roots that do not appear upon the graph. And that was the case here. And just to reiterate, imaginary factors always have imaginary friends. I can't have plus I without having a minus I here. So the solutions to this are plus or minus 2 and plus or minus I. All right, let's do one more example of these before we move on to something else. And this time we're going to start with, see if I can clear this off so we have a clear screen here. Let's start with 3x to the fourth plus 12x squared equals 6x cubed. So there's my polynomial. First step, as usual, put it in standard form. 3x to the fourth minus 6x cubed plus 12x squared is equal to 0. I now need to go back and see what do I need to do in order to factor this. Well, what I'm going to do is I'm going to start off by dividing everything by 3. 3 is a common factor here, and I could write it out here as a factor, or I could just divide everything by 3, since my goal here is not to write it in factored form, it's to find the solutions. So if I divide everything by 3, I get x to the fourth minus 2x cubed plus 4x squared is equal to 0. So there's my next step of my polynomial. So common factor, sure, x squared. X squared times x squared minus 2x plus 4 is equal to 0. And somebody's probably thinking Could I have done that in one step? Could I have just made my common factor 3x squared? Absolutely, it would have worked just fine, because in the next step, when I set this factor x squared equals 0, and I would have divided that by 3, and I still would have had the same solution here, x is equal to 0. So it wouldn't have mattered if I had done that all in one step. But what about this? This doesn't factor, this x squared minus 2x plus 4. It is a factor. I need to set it equal to 0. X squared minus 2x plus 4 is equal to 0. But if it won't factor, how are you going to solve it? Well, how about we use the quadratic formula? I've got this to a quadratic. I have a power of 2, so I can plug it in the quadratic formula. X is equal to opposite b plus or minus the square root of b squared minus 4ac divided by 2a. So I have plugged that into the quadratic formula. Let's start simplifying. I get 2 plus or minus the square root of negative 12 over 2. All right, I need to simplify the square root of negative 12. Let's come up here and do this as a separate step in case you've forgotten. So negative 12 is negative 1, and this is 4 times 3, and 4 is 2 times 2. So I have 2 2's here. The 2 comes out. This negative becomes an I, and then what got left over underneath the radical? This 3. So 2I square root of 3 is the simplified form of that radical. So we can rewrite this as 2 plus or minus 2I square root of 3 all over 2. And I have a common factor of 2 in all of this, so I can divide that out. So this becomes 1 plus or minus I square root of 3. So what are the solutions at this point? What are the zeros? What are the roots of my polynomial? The zeros of my polynomial here are 0, 1 plus I square root of 3. I'm going to make this go down a little so you can see that. 1 plus I square root of 3. Except now I can't find it when I write on it. Okay. 1 plus I squared of 3 and 1 minus I square root of 3. Those are the zeros of my polynomial. I have 1 real root and 2 imaginary roots. If you were to graph this on your calculator, you would discover that this 0 of 0 would give me an x-intercept. These other 2 would not give me x-intercepts. Now, what else do I know about the 0? It's going to have a multiplicity of 2, so that's going to bounce off the x-axis at x equals 0. So we have solved our polynomial by factoring and setting those factors equal to 0. And in this case, we got down to something that wouldn't factor very well, so we substituted it into the quadratic formula. All of those factors set to 0 give me the zeros, the roots, the solutions to my polynomial, and as long as they're real numbers, they give me x-intercepts.